Hello, I'm Kevin Kotzen from AIM Lab at the Technion Institute of Technology, Israel. I'm presenting benchmarking photoplethysmography peak detection algorithms using the electrocardiogram signal as a reference. Photoplethysmography, or PPG, is a simple optical technique used to detect volumetric changes of blood in peripheral circulation. It is non-invasive and can be used continuously. The PPG signal is generated due to pressure changes caused by each heartbeat. In this work, we are interested in the detection of the systolic peak of the signal. The earliest widespread use of the PPG was in the pulse oximeter, which measures oxygenation in the bloodstream. More recently, PPG has been widely used in wearables for the passive measurement of heart rate. Newer devices include the Oura Ring, which monitors sleep, and the Vancell BP band that monitors blood pressure. The market for embedded PPG devices is growing at a rapid pace. The past 7 years have seen per annum sales growth of 30% or more, taking sales numbers from 28 million in 2014 to an expected 600 million in 2021. We monitor cardiovascular signals in order to get information about patient health. Common metrics that we use are heart rate and heart rate variability. In order to extract these metrics from our measured signal, we need to accurately detect fiduciaries. For ECG, this fiduciary is usually the R-peak, the red star in our image, for which there are a wide range of robust peak detectors. For PPG, this is a systolic peak, marked with a green X. The more accurate the detection of these points, the more accurate our metrics. Robust peak detection on the PPG can be rather difficult. The PPG sensor is not fastened to the skin and may move around and shift to a new position. This introduces a high level of noise into the signal, and even a small shift in the position of the sensor can have a big impact on the baseline and amplitude of our signal. The PPG peak is also smooth compared to the ECG peak, and the exact peak location may be difficult to determine. There are several PPG peak detectors in the public domain. While these can be benchmarked using a small annotated dataset of PPG signals, the performance of each algorithm on a specific setting has thus not been available. For example, a peak detector that works well during exercise may not be the optimal peak detector for a patient at sleep. To solve this problem, we developed two measures to benchmark PPG peak detectors using the ECG R-peak as a reference. The first algorithm uses the ECG R-peak to forecast the position of the PPG peak, taking the pulse arrival time, or PAT, into consideration. The second algorithm looks at the accuracy between the instantaneous pulse rate, the IPR, elaborated from the PPG, and the instantaneous heart rate, the IHR, from the ECG. Before we get into each method, just a quick justification for using the ECG peak. ECG peak detectors have been extensively studied, and when a strong detector is used, are highly accurate and robust to noise. There are also validated means of calculating the signal quality index of the ECG, which is useful for removing noisy ECG segments. The time between ECG peak and the PPG peak, the PAT, is also relatively stable and easy to calculate. Finally, the time between consecutive ECG R-peaks should be almost equal to the time between consecutive PPG peaks. Peak matching. To evaluate our PPG peak detection algorithm, we need to know when and where our PPG peak detector is making mistakes. To do this, we forecast the expected position of PPG peaks from the ECG peaks. Recall that the beating of the heart will result in a pressure wave traveling down the arteries and into the periphery. The ECG R-peak indicates the start of the main pumping action of the heart. while the PPG peak indicates the maximum volume of blood in the measurement site. The time between the ECG peak and the PPG peak therefore varies by measurement site, individual, age, blood pressure, and position, so a simple constant value cannot be used for this forecast. So how do we do this? The first step is to detect ECG peaks using both a strong and a weak ECG peak detector. We use both a strong and a weak ECG peak detector as this allows us to detect segments of the ECG with poor signal quality. Next, detect PPG peaks using the algorithm you wish to benchmark. Then calculate PAT by measuring the times between each ECG peak and the next PPG peak. The PAT will be noisy due to PPG peak detector errors, so remove values that are not physiologically possible and smooth the PAT signal using a 10-minute rolling average filter. The PAT signal can now be used to forecast the PPG peak position from the ECG peaks. Simply add the corresponding PAT to each ECG peak and shift it forwards in time. This forecast is then used to classify PPG peaks. PPG peaks located within 100 milliseconds of the ECG forecast are classified as a true positive. This leaves the false positives and false negatives, which are easy to spot. The results are then quantified using the F1 score. F1 is the harmonic mean of precision and recall and punishes extreme values. IHR to IPR accuracy. The IHR provides a lot of information about patient health, physical exertion, and the functioning of the autonomic nervous system. These metrics are well defined in literature and are widely validated biomarkers. When calculated accurately, the IPR should provide much of the same information as the IHR. For this technique, it does not so much matter where the peak is detected, as long as it is rather consistent between consecutive peaks. As before, the process begins with the detection of the ECG peaks using both a strong and a weak peak detector. The PPG peaks are then detected using the algorithm we wish to benchmark. The IHR is then calculated as the times between consecutive ECG peaks, and the IPR is calculated as the times between consecutive PPG peaks. To roughly account for the PAT, we have to shift the IPR signal back by 460 milliseconds. Once this has been done, we convert all measurements from seconds per beat into beats per minute, or heart rate, and add an upper and lower boundary of plus and minus 5% to the IHR. Finally, we calculate the ratio of time the IPR is inside the IHR band and report this as a percentage. We evaluated our PPG peak detector benchmarking techniques on the MESA dataset, which consists of over 16,000 hours of PPG and ECG recordings measured during at-home, unsupervised sleep studies. The patients ranged from 54 to 95 years of age. The reference ECG is a 3-lead ECG attached to the patient with snap electrodes. The PPG signal was recorded at the fingertip with a Nonin 8000 pulse oximeter sampled at 256 Hz. I present tables A and B, which show the results of peak matching and IHR/IPR accuracy on the MESA dataset. The Pulse's PPG peak detector from Lazaro performed best for both techniques, achieving a peak matching F1 score of 0.94 and an IHR/IPR accuracy of 89.6. Our main contribution is the development of two techniques that allow for benchmarking of PPG peak detectors using a reference ECG. On our dataset of over 16,000 hours of PPG data recorded during sleep, the Pulse's peak detector performed best. Our methods still need to be further validated on irregular conditions such as arrhythmia. Our peak detectors should also be benchmarked on additional data sets that have different population samples to those tested. Thank you for your time, and please see our proceedings paper for a full list of references. Please let me know if you have any questions.